Hi, welcome for the lunchtime. I'm Emmanuel Keller. I'm a member of the software engineering team at CyrilDB. And my main topic, you heard a lot already this morning about it, is indexing. And we are going to go in deep inside indexing. So bear with me. It's 20 minutes of checking one by one every feature that is now provided in CyrilDB v1, everything related to indexing. So path to intelligence, part one. I will start with a first concept that is not too much common in typical databases. It's more common in full text search. So you probably are using in the Lucene world some kind of analyzers. So we are bringing to CyrilDB 1 analyzers. Analyzers are tools that manage to process text data, because when we want to do full text search, we need to extract the words from the text. We are using analyzers. So in CyrilDB, it's coming. Yeah, in CyrilDB, it looks like this. So you have this define command that lets you create instance of everything in CyrilDB. And we now have defined analyzer. Analyzer is a name that you choose, and it's made of tokenizers and filters. Tokenizers is this idea of taking a text and splitting it into words. For us as human, of course, it's easy, right? But for a software, we need to guide him to understand how to do that. So in this example of having Rust web programming, we are using a tokenizer called class. So there's two of them, camel and class. So class is the one that each time the Unicode class change, so a space or alphanumeric, then we decide it's a new token. So this is the way we tell CyrilDB that you need to extract Rust, web, and programming. If you want to index code, then we use that kind of things, the camel case or the snake case. So snake case with the underscore, it's already handled by the class, because the underscore is just another class in Unicode. But for camel case, it's going from uppercase to lowercase. So camel is this tokenizer that knows that the case has changed. And then my rectangle becomes my rectangle. So you can use CyrilDB to index your code if you want. Then we have filters. Once we have the tokens, we have those terms, we need sometimes to make some filtering. I mean, we want to maybe just keep the radicals, the root, of the terms. So for accepting, as example, we are going to use the snowball. So it's one of the filter. Snowball is a filter that understands about languages by knowing how terms are usually terminated in a language. And in this case, we tell Snowball that the language is English, and so eng at the end of terms is going to be removed. But also, for accepting, we have acceptance that would be accept as well, accepted that will be accept. So it's a way to make the thing, to have different candidate for different words that will ease the search. Filters, tokenizer and filters. It's what make an analyzer. We are going to see how we use it just after. We have, with version 1 of CyrilDB, several tokenizers. Blank, we split each time we see a blank character. Camel, we just talk about it. Class, we just talk about it. Punctuation, sometimes you want just to split when there is punctuation. Then we have 5 filters. These filters are ASCII. It's like if you want to make a like search, right, we usually remove just the diacritic character, the accent. In English, there is not too much, but in my language, French, there is a lot of them, so we are happy to get rid of them. We have edge-n-gram. Edge-n-gram is the idea of just keeping the beginning of the word. You will use this one if you want to do an auto-completion system, where you want the first terms the first characters to bring up some terms. Snowball, we talk about it. So Snowball comes with 17 languages. So if you have text in different languages, it will be handled nicely. We have lowercase, uppercase. I don't go in details. You understand what it means. OK, let's go into indexes. This is the main thing. There is already one index currently in CyrilDB. Is when you create a record, here we are creating a book, you give a key, book 1, and then the content. Here the content is the title. Book 1 is the key, it's already the index, it's what we call a primary index, right? So this is already present in CyrilDB the way you know it. And it's handy because you can quickly and efficiently find a record by using the key. Primary indexing. In this case, you probably, for the one that didn't know about CyrilQL, this is a nice way to get a record there where you put book colon 1, right, and you get the record. Primary indexing. What we are introducing now is secondary indexing. What does it mean? It means that we are going to be able to make an efficient request by looking for a document based on the content and not anymore just with the key. So it's secondary indexing. In this example, we are looking for the book by the author, and we are looking for the book by the content of the title. You discover here the new operator, @, which means matching, which is the full text operator. Let's go to the full text. How do I create an index in CyrilDB? Define again, right? Define is our friend. Each time we want to create something in the schema of your CyrilDB table or database. Define index, the name of the index, which table is going to be indexed, which column, here it's just title, search, because we are going to do a full text search index, which analyzer I'm going to use, because every text in title are going to be checked by the analyzer and the term extracted and so on. You get it. BM25, the boring part of the sentence, which is this algorithm, this classical full text algorithm that is used by everybody in the search world before vector search. It's another topic. And highlight, because in this case, I'm going to say that I want to do highlighting. I want to have my terms, the search terms, be highlighted in a way, and we are going to see after how. It's optional because if you do that, we do an additional work, so you have the option to enable it or not. Okay. Then we have a unique index, which is a special case where we want only one instance of a document with an ISBN. As an example here is to have a book as an ISBN. It's a unique way to notify this book. You are supposed to have only one of these records, so you tell CyrilDB that you don't want a duplicate of this ISBN in the database, and once you create a duplicate, you will have an error. This is what you expect from this index. So it's a special purpose index. Easy to do. You just add unique at the end of the statement, and you have unique index. As you can see, we have a support from something like schemaless, but it works also with a schema, by the way. But you can index a value inside a JSON structure, right, or hierarchical structure. So we just say edition.star ISBN, you get it. It's a way to go inside and extract one value inside the JSON document. Okay. Standard index. The goal here is to speed up the queries. So in the index, we are storing the fact that there is a term related to this record. It's an easier one to create. Define index, the name of the index, on book, the name of the table, and which fields. Comment about fields, it's a plural. It means you can make a compound index. So you can make an index that will index several fields. And you have also this 3 dot at the end. If the author is an array, and if you look at the record, you can see that we can have several authors for one book, right? So we put that in an array. And when we put this flattened thing, we are just going to decide that all authors are going to be concatenated. So the index is unicity for the whole array. If we don't put them, we take the value inside the array, and each value is one author, right? I should say that there is a restriction station later, so if there is question about those things, I will be able to go in details and give an example as well. Standard indexing and flattening. Okay, so we have 3 secondary indexes. We have full text, we have normal indexes, and we have unique indexes. And it's available in version 1.0 that you can download probably today. Focus on full text. Creating the index is one thing, but it's not enough because we need also to retrieve the records. So for that, we have created the matches operator. It's easy. It's to at, right? And it's a way to say, look for the term REST and web inside title. Difference with equal, right? If it would be equal, then I would have to put the whole title. Here I can just use the terms. It's an AND operator in between. If you want to make a more complex Boolean queries, you can mix them together and split yourself the terms and put or AND. Because the beauty of the thing is that this operator is just an operator like any other. So you can put together any other predicate on serial QL, right? With equal, minus, I don't know, range, start with. There is many different operators that can mix together. These adds take an optional argument. We are going to see later on why. The idea is that if you have several match operators, it's interesting to know which one you refer in function that we are going to see after. Okay, match operator. Highlighting, here's one. Here's one function that takes this reference. Here we are using search highlight to say that we want to highlight the predicate with the reference 1. In this case, we have only one. But you could search in the title with reference 1, in the content with reference 2, and in this case, you would like to highlight either 1 or either 2, or both, by the way, and you would then put 2 of them. It's pretty easy, search highlight. You put it's a tag, a HTML tag, but it could be anything else. It's just a sequence of characters. The first one is what we put before, the second one what we put after, and the one is the reference to the match operator. In the title, you can see that now REST web programming has changed a little bit and and the highlighting has been added. Highlighting. You may not want SerialDB to make the highlighting for you. You want to make it yourself. Then you can use offset. It's the same thing. Search offset. You don't need anymore to give the prefix and the suffix for the highlighting. You just say that you want the information about where the words are, and we give you back this offset, which is the position of the found words in the original text. And it's up to you then to make the highlighting in your code. Okay, offset. Then we have scoring, because of course when we do full text search, we want to sort the result by relevancy. So BM25 is the funny algorithm that provides a score. And we expose this score through this function, search score. So again, you put the reference to the to the matches operator, because you can have several of them. In this case, it's just one. And you have a score, which is the BM25 score. Higher it is, more relevant it is. By default, we don't sort. Remember, we are integrated to serial QL, which means that you have to specify order by. You are in control. You decide if it is sorted or not. So it's just, you sort by score. Score is just the field that we put after the function. Search score as score. You can label it the way you want. It's just a value. Advanced scoring. The idea is that you may have title and content. Finding the terms in the title is more relevant than in the content. So you have two scores. So here we have the situation where you have two match operators with reference 1, reference 2. For reference 1, we say that the score is 2 times bigger than reference 2. Again, it's a function that you write in the select part of the query. You are in control, and you decide the way you want to compute the score. We are going to provide in the documentation some example and to help you in building something relevant. But it's not different than what you will see in typical search platforms. At the end, you have a score that mixes together several fields. Good. We have indexes. We have the way to query and use these indexes. So we introduced something new that was not existing in SerialDB yet, is the query planner. The query planner is the guy that say, okay, I have an index here. You have made this query with all those predicates. Now I have to understand if I can use an index or not. So the query planner is this first version of the query planner that try to trigger the indexes and speed up the queries for you. Query planner. With the query planner comes a new parameter to select, explain. So I believe you are you are already familiar with this logic of explaining a query in SQL database. In serial QL, it's explained at the end of select. And you have an explanation, an explain plan, you name it, where we explain if it is or not using an index and how. So in this case, an index has been identified. You have the name of the index, a table concerned by the table blog. Index is FT title, and the operator is at. So it used the one related to the full text, right, Resource 12. So you are in control. You can see what is happening. If no index is triggered, then you are in SerialDB before 1.0, and it means that it's going to iterate over the whole records. We call that table full scan. It can be really handy in SerialDB, and you can see that in the explain. So again, if you want to see if you are using index or not, explain. Table iterator. You can also have control on the query planner. You can guide him in some way. So you can tell him, because we had two indexes, right, in my example. We have one for the full text, one for the author. So we may use one or the other, but you may know that the cardinality is more interesting on one of the field or the other, which is a typical way to improve a query. So you can tell the query planner to use, by preference, one index. If it's not possible, it will fall down to what you think is better, but if it's possible, it will do it. So in this case, we say with index, the name of the index, and that's it. It's using the index you wanted. Great. Sometimes you also don't want to use the query planner at all and don't want the index for many reasons. So you can tell, no, please don't use an index. I know what I'm doing, and don't use it. Explain. So you put with no index, you have the explain, and you know that the table iterator is using and not your index. You're in control. Okay. Another thing which is about getting information about the index. So the thing to know about index is it slows down ingestion, right? Because when you put a record inside, it's going to update the index as well. It's a normal thing. And sometimes you need also to understand what is the impact of the index on the database itself. So we provide now a new command called analyze. As you can see, it will probably be used for other things in the future, but it starts with the index. So you have analyze index, you give the name of the index, and we give you this low-level, little bit information about what is happening behind the scene. Okay, index statistic. So in summary, the summary for indexes, we have analyzers, we have three types of indexes, standard, unique, full text. We have this flattening logic, we have this the ability to index sub-field or sub-values. We have the matches operator. We have three search functions, score, highlight, offset. And we have the query planner that gives you the control with and the explain plan. Yeah, nice. I think there is many things to do with this. Next, vectors are not directly related, but there is an indexing part on vectors. So vectors, we really believe, of course, in everything which is happening with AI today, and for ages, I mean, for ages, not too much, but from the beginning, SerialDB is able to store arrays and vectors. So we wanted to leverage these capabilities, and I think there is no better platform for storing a huge amount of vectors, because this is really easy to use. So the first things we had to do for you to be able to use this stored vector was to create functions. So first, the way you store vectors in SerialDB is really easy, right? You create a vector, it's just an array, right? Just put your value. It can be, of course, numeric floating values if you want. If you want to retrieve this vector, it's as easy as any other field. So pretty easy to use. But the next thing you want to do is manipulating these vectors. And here, it's an example of how you're able now to manipulate these vectors. So if you have millions of vectors in a distributed SerialDB instance, and you want to apply a function to a set of vectors, you can do it. You can do it with update vector set object and use this new set of functions that start with vector column, and you can update your vectors in the way you want. Vector add, but not only. Vector add, vector angle, vector cross, vector divide, vector dot, vector magnitude, vector multiply, vector normalize, vector project, vector subtract. Oof. Okay, so if there is something missing, just tell us. We want to add some, right? And we want to know what you are going to build with. So yeah, definitely. Vector functions. But it's not enough. We also have some distance computation. We have Chebyshev. I'm sorry if I'm not pronouncing it well in French. Euclidean, Hamming, Manhattan, Minkowski, Cosine, Jacquard, Pearson. I'm not sure I know what they are useful for each of them, but I know that you are going to build amazing AI stuff with those. Right? So those function can be applied to any vector in your SerialDB table instance or whatever. Okay, so how is it related to index? So once you have vectors in the database, then we want to query them, right? So to query them, we have now a vector search. So what do we do? We have implemented a new kind of index based on a scientific paper called symmetric M-tree. So if you have a look at the scientific paper, you will see that it's exactly what we have implemented. And remember, SerialDB, the code source is on GitHub, right? So you can have a look and see if we did it right. Recently in Lucene, they did it wrong. Yeah, anyway. So create vector, an example of it works. You create vectors in your database, and you create your index, define index, as usual, name of the index, on vec, it's the name of the table, the fields object, and then you said M-tree, because you know that you are going to use M-tree. I will explain after why. The dimension of your vector, because we need to know that in the beginning, and which distance you are applying, and of course, every distance and similarities we have seen before can be there. So your index is able to work in any of the distance or similarities function that you have seen just before. Symmetric M-tree index. Why is M-tree useful? It's useful because it gives you an exact NN operation. Sometimes it's called brute force in some other environment. When you want to make an exact NN operation because you want to validate your model, then you may use brute force, which can be really slow. So we didn't make any brute force implementation. We decided to go from an indexing that supports exact NN operation, still pretty fast, not as fast as the other one that we're going to see after, but you can already validate your model and make it work a little bit slowly, but fast enough probably for validating your model. It's easy to use, a new operator. It's so as you can see, where object, we have less than, greater than, a reference in the middle, and the operator that is supposed to be compared in terms of distance with your millions of vectors in your database. And it returns, the 2 is the key NN, right? It's the number of closest vector according to the distance or the similarity you have chosen. And here they are, right? And it's pretty fast. Exact NN operation. This is available in SerialDB v1, so the one you can download later. It's there, you can play with. There is one limitation, which is you cannot make deletion, which is normally not an issue yet. So we are going to fix that. It's not yet there. But when you create a model, usually you have your vector, you put them there, and you don't need to update them, right? If you need to update them, you are going to put a new full model of vectors. So at least you can start playing with. So it's not yet in V1, it's going to be in V1.01 probably. So in a few weeks, you are going to have another implementation, which is the one you would like to use in a production environment based, this is KNN with distant projection. I was talking about the next one, which is approximated NN operation based on HSNW. So the one of you that use already KNN or ENN operations know that it is the algorithm that optimizes and is faster. But is approximate enough for many AI applications. So this will be available as well, and it will be a different index. The only difference is you put HSNW in the definition rather than M-tree. Just come back in distance projection. When you do your KNN request, you may want to see the distance. So printing the distance, it's just using a function, right? The function is here, vector distance Euclidean, and then you see the real distance, in this example, 2 and 4. Okay, I think we are there. You're still with me? Vector summary, 18 vector function in total, and more if you ask us to put more. 5 distance, 3 similarities, M3 index that are already fast and available in V1, HSNW available in few weeks in an upcoming version. And that's it.